is like, maybe that one doesn't have like a volume. Right, that one's wrong. Anyway, maybe this thing was turned off. I don't know. But we didn't hear it say, when I said record, we didn't hear it say record, right? Usually it would announce that. Wonder if there's something. Anyway, it worked the one day, but maybe it'll work today, hopefully. Let's see. Here. So yeah, I graded homework one. So and it went so one group got 99, one group got 0, but the 0 group got a like they just copied for the first question, they copied Wikipedia and pasted it in. So that's like an automatic 0. It's kind of like no questions asked plagiarism thing. So but all right, if you're an undergrad, right? Or if you're a grad, then there's like 13 grades plus the final counts as 4. So it's like 17 grades. Plus if you do the questions in class. So basically a 0 on one homework isn't going to hurt, I don't think, And then if it does at the end, like in May, just email me and we can figure out, what's fair or whatever. You know what I mean? So it's just like it's kind of like a rule I said at the first day in class, like, and you have to check the other guy's stuff. So if you're a group, you're responsible for the whole group thing. So it's just I would just take the 0 and like move on from there and just don't really worry too much about it because I don't think it'll matter. If it matters in the end, just come to me in May. We'll figure it out, like I'll fix it, So, but right now, just take it and then otherwise, it's kind of a free for all, And you can't, like, I can't grade Wikipedia, and it's also like bad to do that, etc. Right? So anyway, so I'm not really comfortable being a cop, but basically it's cop situations like that, but you got to do it, I guess. I don't know. Anyway, so anyway, so this, yeah, that homework and also this one. So I wanted to just say, like you have something like what's molecular dynamics, and you have no idea, So just go to like one of the AI things, not the Google one, um, but one of them. There's many now. I only use the one, but oh, this woman's, I don't know, you have to, it's $20. She's given a talk and there's a dinner. She does simulation stuff. So she's a Schweitzer student. Oh, sorry. I thought I just did that. Oh, all right. It's got this, which one is it going to project deal?
I think most probably it is duplicating the screen.
No, it's a new screen. It's a different screen. That means it's duplicating the screen would be a nice feature right now. That's what I was assuming it would do. System settings, like display, maybe general. Let me try this for a second. Or I just noticed this, but it doesn't really matter. I can move it here. Anyway, so yeah, she's given a talk. It's like a Thursday. I can send that out to the class if anyone's interested. It's directly related to this class, so I might try to get her to come here, like to come to UC and give a talk. Anyway, I just got that this morning. Oh, what I wanted to do was just say like if you, all right, so I can go here. So like just like you can just put in a question, right? So we had, let's see, like here's this week's thing. Right? Oh wait, this is pretty confusing. I can just use that. So like uh let's see, so these aren't really good, but you can actually just type in the name of the paper. Whatever, I put the paper thing, just copy that whole thing and put it in there. Then say like whatever they did. Just kind of ask the question, it'll give you a pretty good answer. Let's see, let me get last week's. This is confusing. Two computers. Oops. Last week's homework. So oh yeah, so like this one's a classic, like what is a molecular dynamic simulation? But wherever that is, you just put it in and it like gives a pretty good answer. That's the wrong thing. No, where did my chat GPT go? Like he doesn't have to be correct, like then it gives really pretty good answer. It's like I think some people did this, right? Some of the answers were like physical movement of atoms. It's like loosely right. I guess I'd like you to say, all right, so it's called molecular dynamics, but it's used basically it's spheres moving around. So spheres could be like, if you put in the right potentials, they could be like rocks. So you can do molecular dynamics simulation of rocks on a beach moving around with the waves, right? So they don't have to be molecules. And in polymers, so they're going to be larger things. So it's called coarse graining. So you collect, like say, a bunch of monomers and make like a Kuhn unit, and then it becomes like a stick. And you have a potential field for how the sticks interact. So it would be stick dynamics at that point, right? Or it could be, if it's a colloid, then you have spherical colloids with charged potentials against each other. So then it's another kind of ball potential, or it could be cylindrical things, right? So when it says like, so you have to kind of, but basically this is so the thing to learn from this is like, look at how it breaks apart the problem. So you ask some question, it goes back to the root question of like, what is this thing? And then it lists it gives numbers and says like, it breaks it into like a list of things, makes it really easy to read. It goes to like all the ramifications of it. And then finally it gives like a summary. So it's like an hourglass. So it starts with a broad thing, like what is the general thing? And it kind of narrows down to like this thing and that thing and that thing and that thing. Within those things, it gives a very coherent like list of whatever. Then the final thing is like it broadens back out and says like you can leave with this. So that's how you should write things. So it's teaching you how to write things. So it's an algorithm. So it's an algorithm you should pick up. Like you should do the same thing. And then also like it's basically right, usually like really pretty close. So it'll give you a good hint if you're like totally blindsided by the question, it'll give you a pretty good hint about it. But then you have to go back. So don't look at this and go back and write your own from your brain, like a blank sheet of paper, and write your own stuff. So it's kind of teaching you something, but you can't just copy this and put it in. I think I can tell if it's a good AI, you can't tell. But if it's like Chat GPT, you can tell that Chat wrote it because it's got a rhythm to it that you can feel like, oh yeah, I remember that beat, So that's that song, that's that band. So basically, each one of the AIs has a different flavor. So I only have used Chat GPT, so you might want to use a different one if you want to get away with that. But basically, what it's doing is showing you how to write an answer to some crazy question, some blindsided question. So if you did that, you could do that whole quiz just doing that, and it would give you like perfect answers pretty much, When it gets more specific in the paper, actually put in the title of the paper. Like, see if I can figure out where this thing is now. Like, here's the title of the paper. Like, it's this thing. So just take that. But maybe you guys already know this, maybe this is just teaching the whatever. Actually, I'm thinking of a swear kind of thing, but let's see. So put in that paper and then just say like, what was this about threading? Why did they use minimal surface. And then it'll come back, let's see, did I do it right or? Oh, scroll down, yeah, right, no. Oops, wrong computer. No, it didn't get it somehow. It's not there, right? Like put in that paper. Let's see. Oh, all right. Well, it's tough when you have two computers here. Okay, yeah. All right, so it's writing it, right? So it answers it. It'll do like in their study, employed, thread and unique topology. I mean, you can learn a lot just by asking it questions. It's clearer than the paper sometimes. Most of the time, it's much clearer than the paper. Like it can resolve kind of what's going on. So it's useful to use it. I haven't actually used it for that, but basically when you're answering questions like this, if you paste in the actual paper thing, it can get it. If you asked it for references to back up whatever it said, it'll give you references. They'll be like made up references. Like it'll be names that look like real names and institutions that look like real institutions and journals that look like real journals. And the title will be a good title. It'll have a good year and good volume and everything. Then you go, oh, that's great. I need that paper. You go to look for it. And the journal doesn't exist. The institution doesn't exist and the people don't exist. But it all sounds like the perfect thing that you need. So that's a caveat to this thing. Like it's just, it doesn't have any idea what it's doing and it's not worried about the truth at all. It's just like doing some algorithm and it works great, but all right. So anyway, I thought I'd mention that. It's kind of a little bit, but and again, you guys probably know more about that than I do, but basically for this class, basically for a lot of things, it's like a good way to go. And what you should get is like learn how to write a coherent answer to something. Like it's going to come up with like the framework. Look at how it framed it up and like how it presented it. And like that's how you should be thinking about answering things. It's appealing to the people that don't understand something that, so anyway, so there's that. Then what else? Any other stuff with this? Scaling factor. So people didn't get a lot of things in here, like the scaling factor. So the random walk idea is that when I did this, showed you the simulation, it does like one walk, another walk, another walk. All of them are asymmetric. So this asymmetry factor for each of those walks would be like 0.8. It could be almost like a rod sometimes, and sometimes maybe a little bit smaller, but never zero. It's never symmetric, right? So that means this idea that it's a random walk, it should be asymmetric. It's naturally asymmetric. How asymmetric is kind of questionable, and what value that asymmetry thing has, that's another issue. Like it's not a normal kind of descriptor for polymers usually. So it's good if you're doing computer simulation because you have the individual molecules and then you can get the asymmetry of each molecule. But if you're doing any analytic measurement like rheology, you don't have an access to asymmetry. So only if you can draw the molecule can you get that number. So you have access to things like the rate of gyration or the end-to-end distance, hydrodynamic radius. Those are average numbers over the whole system. You can model that average number versus the molecular weight, and then you can get this power law dependence that shows that it's Gaussian, but you can't get the asymmetry, unless you do the simulation. So, and then what do you do with the asymmetry is another issue, So, if it's something that you can't actually see, in other words, does it impact rheology if you can't measure it with rheology? Maybe it does, I don't know, but basically it's a number you only get from computer simulations. So anyway, so you don't expect them, you expect the random walk to be asymmetric, quite a bit asymmetric. And then how asymmetric is kind of because you don't really know how to control. There's not a scaling law for asymmetry. There's not like NL squared. It's just like a number. So a bigger means more asymmetric, smaller means less asymmetric, but basically not a number that's like analytic. So it's analytic in the sense you can measure it, but not in the sense that it's got some theory that goes behind it. So anyway, so there's a lot to that, I guess. Only simulation people really talk about it. So then anything else? There's quite a bit here, actually. The idea of stiffness. Okay, so stiffness we'll talk about pretty soon, maybe partly today, but basically the local chain, like if you have a conjugated chain, like polyacetylene, say, and you're going to just have double bond, single bond, so it's a rigid chain, or a protein that's got charges, and then the chain's rigid, right? So that's a stiff chain. And then how does that affect this size of the chain? Well, if stiffness is going to increase the step length of the chain, right? So you had your is this going to work now? That's the question. Lights on. That thing's there. Let's zoom out. All right. So you have, we're saying you have a Kuhn chain, and we have, these are freely jointed bonds, so we can go anywhere, right? And then stiffness is going to be, so this what do you call it? Not stiffness, he called K or something, or it's like K something. Anyway, so that's just going to be like increase LK. I mean, they're going to increasing the stiffness is going to increase LK, right? So you say it's like NLK squared is R squared, RG, or end-to-end distance, right? So basically, and there's also a thing called a contour length, which is going to be the number of Kuhn units times the length of the Kuhn units. So it has to also equal the number of chemical units. Right, this is actually usually L. Chemical units tend to length of the chemical unit. So the chemical unit would be like 1.54 in length for polyethylene and 6.7 angstrom for the Kuhn length, right? So NK would be kind of whatever N chem is divided by 6.7 times 1.54 would give you like how many Kuhn units, right? Because C has the length of it, the contour length has to be a fixed number, because the chain, if it's fully stretched out, has to be the same length, no matter what unit you conceive of it being made up of, right? So anyway, that means that this R squared is actually L times some unit, some size unit, this Kuhn unit, right? So basically, there's two numbers, the contour length and the Kuhn size are the two numbers that make up the size of the thing. And this is going to be like the square root of that is going to be the square root of these things. So you get it in a little length. So if you increase the stiffness, well, it's still going to be, so this means it's still in L squared, just L has changed. The contour length is the same, L has changed. So basically, this size is going to just be proportional to the square root. Our square root of R squared is going to be proportional to the square root of the Kuhn length, which is kind of related maybe to the square root of this K thing. So yeah.
Is it R being multiplied by another exponent on the outside? The R squared.
Oh yeah, sorry. This squared should be inside the average. So it's average R squared square root.
Okay, so it's R squared, then it's being the 1/2 power.
Right. But that gives you kind of a length. I mean, it gives you the dimensions of length. The thing is actually a variance, right? So this is the standard deviation of a distribution. So it comes out with units of length. So it's important to keep in mind that it isn't an actual length. So you say like 2 times that is the diameter. That's pretty commonly seen in papers. Well, that's kind of crazy to say that, because it's not a length to begin with. So 2 times that isn't really a diameter, really, so it's good to kind of figure out. So yeah, you'd use it like what I'm going to pick, like I see a micrograph and I see this thing and it's 200 angstrom, TEM or SEM or something. Then like, could that be a coil? Well, yeah, RG is 100 angstrom. Yeah, it could be a coil. That doesn't mean that that's the actual diameter of that thing you're looking at, right? So I get into that a little bit more today, but anyway, so basically the stiffness is going to just directly increase the size, right? So So there's kind of these relationships that connect it together. Anyway, so, you know, I didn't expect you to go into that detail, but basically if we make it stiffer, it should get larger. But in this paper, they have the cyclics, it gets stiffer, it gets smaller. And they don't say like, oh gee, that's kind of weird. You know, like that's the opposite of what you'd expect. So stiffer should make it bigger, and they're getting stiffer and smaller. So it could have something to do with being a ring. I mean, maybe the topology of it makes it kind of, I don't know why it would get smaller. If it got stiffer, it should get larger. Bottom line, right? So they don't mention that that's like a problem. So that's a little bit of a thing in this paper. I mean, there's a lot you could go through here on this guy, but so I think that any questions on that homework one? I mean, I already kind of briefly went through one of the, yeah.
Stiffness like the angle between the chain.
Yeah, it could be stiffness. So I'll go through this, but basically, yeah, let's see. This guy, no, this guy. So what, yeah, what's going to be the stiffness? So we start out with a Kuhn chain or a freely jointed chain, right? So I have total freedom. Then I say, oh no, this has to be 109 degrees if these are carbons. That's a fixed angle, and then it can spin around this, right? So that's a freely rotating chain. So that thing, so let's say this had a Kuhn length of 1. This thing I think has a Kuhn length of like 2.2 if you put in that bond angle. And then, oh, these things have things sticking off. So when I rotate around that, if I look down that chain, so I'd see something like this. This is called a Newman projection, but it's like eyeballing down the chain. Then I see like this carbon has 3 things sticking off. One's a polymer chain, and 1 and 2 are the side groups, which could be, if it's polyethylene, they're both hydrogens, right? But basically, when I'm doing this spinning around for freely rotating chain, that hydrogen is going to come on top of the polymer. That's going to be energetically not favored, right? So that means it isn't freely rotating. It's actually a rotational isomeric state chain. Rotational isostate model, sometimes like prism, right? So that's fluorine. Right, so then you can get a better number for that. If you do that, you get the something like 5 for the L if you started with 1. And then there's other factors coming into play, like other kinds of things that would restrict it. They'll get you to the 6.7, whatever for polyethylene, right? So anyway, so you can kind of go through a sequence of things that you want to think about, or you can just say like, oh, I have a random walk on a Cartesian coordinate system, right? So I can go here, I can go there, but I'm not going to go backwards, right? So if it's a total free walk, it can go in any direction. If I don't go backwards, that Kuhn length goes from 1 to 1.2. I'll show you that later on, but basically, just not going backwards on a walk on an XYZ coordinate system increases that's a stiffness factor. So that's the simplest kind of stiffness. Like you can't walk on yourself. It's excluding the previous step. Right. So there's, yeah, so it's the bond angle and the bond rotation. And then also if you have a protein and then you put charges on it, well, those charges repel, right? So there's a Debye screening length for the charges, and basically if they're spaced together less than the screening length where the charge effect isn't seen, then that will stiffen the chain. And so charges can have a huge effect. Most biopolymers are going to have huge persistence lengths. Yeah.
Since it's a freely rotating chain, does the bond angle remain the same or need to change?
And freely jointed, there's no bond angle. It's just like it's a free for all. They're just floppy connected rods. Just like if you took a chain links and just threw it on the table, so they can do anything it wants. Like the model would be like, draw, like you have these things and then they just hook together like a chain. And then that can just fall apart and crumple it down. So it's a chain in each of the units as KT, it's being pushed around. That's the freely jointed chain, which is the Kuhn model. That's the NKLK is R squared. Right, that's freely jointed. Right. And then so it turns out you can model any of these complications and just get back to the Kuhn thing. Right. So you can get back to that and just say all these things do is just change the LK. Yeah, there's this effect, but basically in the end, there's an LK that you can measure with rheology or with scattering. And then that's the LK, it's a physical number. And all the stuff that you piled on doesn't matter. Right. So that's kind of how that thing works. But yeah.
For the cyclic, the threading number, is it going to change the Kuhn length of the cyclic?
The Kuhn length is really independent of most things that you think would affect it, like temperature doesn't affect the Kuhn length. So you think that would affect it because the rotation would speed up or something, but it doesn't. So it's temperature, basically temperature independent.
I mean the number of threading. Sorry.
Yeah, but so threading doesn't affect it either. I mean, this kind of like concentration. So you take a melt of polymer or you take a dilute solution of polystyrene, say. So you have a Scotch tape container or you have napalm, which is polystyrene and gasoline, right? So basically the Kuhn length in those two is exactly the same. I hate to give bad examples of polymers being used as weapons, it's like, but basically, it's true. So it's kind of like the Kuhn length is the same, even if you put it in dilute solution. So yeah, the Kuhn length is a fixed number. It's strange. You think it would have all this variability, but it doesn't. It's just the chemical structure, the charges, that's it. It's not impacted by the other stuff. I mean, there might be some slight, very slight, like a percent change or something like that, with conditions, but. All right, so that's that business. So hopefully, any other stuff on that homework, the one or then the two, two. All right, let me just, waste the whole class here, but two people are asked, one person asked, and it's a logical thing to ask is, Einstein's 2.5 thing, right? So the Einstein figured that out for Sears, and he said, like, afterwards, someone interviewed him and said, "Was there anything he did that you wish you hadn't done?" They said it's this equation, yeah. So the viscosity for a composite is the solution viscosity, and then the concentration times 2.5. That's Einstein, although he doesn't wish to be known for that. So anyway, so you can see this, like the modulus. You see that equation, viscosity modulus, the shear modulus, same thing. So everyone just uses that equation for any kind of constitutive parameter. Constitutive means you have a perturbation. So kick the dog, and then the dog barks. There's a number that relates kicking the dog and the number of times it barks. So it's a total non-understanding equation. It's just like an observation. It's an engineering equation. So those are all called constitutive. So any constitutive parameter like modulus, shear modulus, just pop in Einstein's thing for composite, and then you're good to go. That's what people do. So, and then if you want to get more complicated, like at higher concentration, you add in like a chi-squared term with some like 6 point something, and you can add in cubic terms. If you look at this thing, if you have 1 plus k phi plus k phi squared by 2, that thing is the same thing as exponential of k phi. Okay, so basically, you'll see something like viscosity equals times exponential of k phi, which is the same, it's kind of the same equation. It would be like k is 2.5. Right, so you can take that, so you can do a lot of little twists with the Einstein equation, like just use math to kind of write it a little bit differently, and it's the same thing. All right, so where does this come from? So if you go, all right, so if you go, you have the shear, the viscosity, and then you're looking at the strain, the rate of strain is the change in velocity dy. So you have this geometry, this is xy. So it's dfx, d area y. So like, in other words, you're putting a force that way and it's being applied to the normal to the areas, like it's a XY thing. Right, the area, it's a deck of cards, you're pushing the top card that way, the area is the card. Right, and that's way you're going is like that, right? And then this is dvx in the direction of the force, that's force x, and then dy is y. Right, so yeah, that kind of geometry. So you say like, all right, so I had my fluid, and then I'm going to add in bricks. So the bricks are just going to make a wall here, right? And then I no longer have y. I have dy times 1 minus the fraction of bricks that I put in. Right? That's a displacement. You displace the fluid, dvx, viscosity, and that guy. Right? Then you say, well, this is my original polymer viscosity. So what am I going to do here? So I say, well, I can rewrite that tau times 1 minus phi equals the original viscosity, and then my original dv dy. That's my original gamma dot xy. Right. And then I could say like 1 minus phi is exponential of minus phi. That equals 1 minus phi plus phi squared over 2 minus phi cubed over 3 factorial. And it goes on like that. So basically, if you take the first two terms, that thing's exponential minus. Let's see, how did I do this? That goes up there. And then if I pull that over here, so then I'll have tau is viscosity exponential of plus, because 1 over exponential minus is exponential plus, then my gamma dot, and that's my new viscosity. And the expansion of that guy is viscosity times 1 plus phi, which is the 1 plus 2.55. In other words, the 2.5 comes because of spheres, not bricks. Because spheres, when they pack, make like a HCP, so some kind of extra holes in it that displace. It's a displacement law, regardless of what the number is here. You've just taken the fluid and displaced it by the solid thing that doesn't flow. That's why Einstein thought it was stupid, because it's just like, kind of like, it's too simple for him. Like he wanted something more. But nonetheless, this is like one of the most popular equations, like for modulus. Anytime you have composites, that's the first thing. Random composites, not fiber. So anyway, so that's kind of, yeah.
Where did that gamma dot come from?
Gamma dot is the shear rate. So
Okay.
yeah, I just put it here. This thing equals so gamma is dx dy. In other words, the shear strain. Then it would be dx dt. So gamma dot would be dx dt dy, and dx dt is dv. The dv dy is gamma dot. And that means that if you, like in laminar flow, so you have oops, there's something there. You have this, and you have a V going here and 0 here. So it's basically the gradient here, like in laminar flow. That's the slope of that is gamma dot, the gradient of viscosity, gamma xy. Right. So anyway, it's good to kind of put a picture of what's going on and figure out. Anyway, that question could get you can understand what viscosity is, like a little bit, like just what's going on with it. So anyway, someone asked that. So that was what I sent them, more or less. But all right, let me get back here. Put this guy back up. Let me get back. Anyway, so if you have questions, just email me and I'll just give you the answer basically, or whatever, So let's see. Let me get back here. I know this is on the computer somewhere, but it's easier to just kind of find it here. let's see, so we get this stuff, all right, yeah, so we got, let me just skip through. I did that, I'll kind of get back to that. This, I'll mention this again in a minute. This business is kind of what I was just talking about. I mean, all right, there's another kind of chain without the sticks. It's just like a pathway, like a squiggly pathway. They could say that's the chain. And then in that case, and I'll go through this a little bit more. So that's called a persistent chain. Yeah. So in that case, so this is like basically biology. Biologists kind of use this. So you say the chains like that. So crack key, I think. Let's see, no, porod. This is porod chain. Porod was a scattering guy from Austria. Anyway, so see, and Cracky was a student. So Porod invented it, and Cracky kind of popularized this, I think, as far as it was like the 60s. So I don't really, but anyway, I think that's how that works. So anyway, he said like you could take this and say there's like a tangent to it. And you could say, well, like you could kind of think about some angle where you'd say that it deviated from it. It's not going to be 0, it's not going to be 10 degrees. So it's going to be something like 6 degrees. And then you'd say like, well, that thing is going to be kind of our persistence length. And this comes from the idea of the theory of a kinetic theory of gases. You have, when you have a gas flying around space, so it's got a certain, and it's going in a random walk, and it's got a certain distance that it travels in this straight line. That's the persistence length of a gas atom. So this walking thing has also a persistence length. And it turns out, and I'll show you, I'll derive that this is 2LP equals LK. So there's a relationship directly with a Kuhn, who was a Swiss guy, I think. So like the Swiss and the Austrians are kind of compatriots, but so those are the two lengths. So I'll talk a little bit more about persistence length. Like there's an equation with it and things, but anyway, so I just mentioned that because this list has persistent chain in it, which is really the porod chain. The rhizome, which is restrict the rotations, freely rotating, freely jointed. Worm-like is a lot like the persistent. Worm-like is the same as persistent chain. And Kuhn chain is the original, kind of the original Kuhn-like thing. Anyway, so did that. This is last time. All right, so then we're here. So we have this equation describes the end-to-end distance of the chain. So we have, let me go back there. So if I do my I'm gonna do my computer program, I'm gonna do walks. I'm gonna get some walks like that, some walks like this, some walks like that, fully extended, same end, right? But I just let it take a random walk. It's gonna go wherever it wants. Sometimes it happens to say like left, 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 left. Then I get a straight rod, right? So I'm gonna have a distribution function. Let's say I say the probability of some length r, and on average, since it can go that way or that way, it's going to be peaked at 0. And then it's going to go down, right? And then it's going to be bell-shaped. But it's going to terminate when I get to the contour length, L. So NK, LK, that's as big as it can get. It's got a fixed length. It can go plus minus L. Otherwise, this thing is a perfect Gaussian. So Gaussian means that left and right doesn't matter. So it's exponential. It has to be x squared. And then you divide by 2 sigma squared. That's the Gaussian. And then if you integrate that from 0 infinity plus infinity, you can get a normalization factor out here. That would make the integral of it equal to 1. The integral, that thing equals 1. The normalized Gaussian. And we said that this sigma squared is NL squared. Or yeah, NL squared for our walk with the steps. So it's a bell-shaped curve. So that's a probability function. It's a probability of finding a chain that has an end-to-end distance r, right? So it's kind of important to say like what that thing is. So that's this. This is the normalization function. That's your 1D Gaussian. or three, this is, all right, so 1D Gaussian would be 1/2. And if you, so the probabilities multiply, so 3D Gaussian is 3/2. Because when you have something to some power and you raise it to the power, you just put the power into the argument. Right? So XYZ would be 3R over 2 sigma squared. Right? So that's the 3D probability of finite chain and in distance R. Normalized to 1 for minus infinity to plus infinity. And it ignores the fact that there's actually a limit because a Gaussian actually never goes to 0. It goes to infinity. So basically, this isn't a perfect function because a chain can only go so far. Right? But basically, it's a good approximation. And it makes the math a lot easier. Right? If you put in that limit, then everything falls apart. So there's another equation that's an exponential that kind of looks like that. That's called the Boltzmann probability. If you have some random thing going on and temperature, there's a temperature barrier like in flow where you have to overcome interactions to have the thing flow. Or if you in this case, this is the energy of the chain, like the energy to stretch the chain. Right. So you have a barrier energy. The probability you're going to get to a distance R has to do with the energy that it takes to stretch the chain divided by KT. That's the Boltzmann. So this is basically an entropic chain because I could say that the energy is log of the probability times KT, which is Boltzmann's law for entropy. Right? That's entropy would be K times exponential of the probability. Right? So that's a chain that has no interaction, no enthalpic interactions. It's just entropy. This is Boltzmann's law is an entropy equation. So E here is actually S, or S times T, right? So, or minus S times T, I guess. But so anyway, so you have that equation, and you're saying because of random walk, it can pass through itself. Like as a Brownian motion, the Brownian path can pass through it. That means there's no enthalpic interaction at all. If it can pass through itself, there isn't even an excluded volume interaction. Like it doesn't have any enthalpic interaction, right? So this is an entropy chain. This is also an entropy chain because it's a random walk. So you say, okay, what's the energy of the chain? Well, it's just like the energy of the chain is just gotten from this. It's KT times that thing. They're both negative, so you can get the energy of the chain. So, I mean, that's pretty kind of interesting, but like why would that be important? Well, if you look at like the force, like how much force does it take to stretch the chain? Well, force times distance is energy, so that change in energy with distance is the force. So if you change the distance, stretch the chain, and the force is that thing, that means you can just take the derivative of this energy that you got by just comparing these two things, and you get the modulus or the spring constant for the chain. Right. So that's the energy, that's a force that it would take to stretch a chain. So it's like, when would you want to know that? Like, when would you want to know the force to stretch a chain? So let's see. So this is one case where you want to know it. Like you want to know, you have a rubber that's made up of chains. They're like cross-linked together. And then you want to know like, well, what's going to be like the force to pull the piece of rubber? Well, the chains that you're looking at are these between the cross links. So it's called the MC. So you'd say that force is going to be the extent that you draw it out, like delta length times this 1/3 or 3 KT over NL squared, N being MC. LK squared, right? For MC in terms of Kuhn lengths, LK squared. Right, so that gives you the modulus of a rubber. It tells you that, so it's kind of strange, the modulus would increase with temperature. Okay, so if you have a like a rocket seal or something, right, and you're going to send the space shuttle into space and it gets cold out, then that thing becomes brittle. It gets a higher modulus. Let's see. Now the rocket seal isn't the best thing to talk about. If you put a rubber band and then it gets hot, the force gets less. Let's see, it gets hot, the force gets more. So it pulls in as it warms up. So when you first start the car, it squeaks. And as it warms up, the squeak goes away because the rubber heats up and stretches back in. If you make a balloon, so this is an entropic loss. If you make a balloon that's filled with a gas and you increase the temperature, the force pulling in by the balloon matches the force pushing out by the gas because they're both entropic. It's an ideal gas, and then the balloon doesn't change size. If you put a balloon in an oven, it doesn't change size. Things like that. So there's a lot of little nifty things about this temperature dependence of the modulus. And then the bigger the chains you put in, the more floppy the rubber is. So if you want to make a gooey rubber, you use like 100,000 K molecular weight chains. If you want to make a strong rubber, you use 10 K molecular weight chains. So the smaller the molecular weight, the stiffer. And if you want to make like an epoxy, you use like 1 K. So this is like a rock. I see. So the molecular weight dependence is kind of the opposite. We think a big molecular weight would be strong, but actually a small molecular weight's higher modulus than that. Yeah.
So is that due to the more crossing links on like the smaller polymers then, where they can get more interconnected beads?
Yeah.
Okay.
Yeah, I mean, you can think about it in more interconnected, or you can think about it, the modulus of the chain goes way up when you have the smaller links in it
Okay.
because of
Yeah, that
this,
makes
you
sense,
know. Yeah, so the other place you can use this is in so this is like a pretty simple thing, but it's got a lot of ramifications. So we had yeah, this thing. So we had the plateau modulus, which is the entanglements, right? So sorry, yeah. Sorry, I didn't hit project. I hit PC, it shows here, and I have to hit the project too. Like you have to say Simon Says. So anyway, we got this. So the storage modulus is the circles, and this is the loss modulus. So they cross, it becomes solid. So it's a rubbery solid, and there's a rubbery plateau. And that's caused by the entanglements. So you have a modulus here that you can measure pretty easily. And then that modulus is going to tell you the molecular weight entanglements. Yeah.
For the force equation you showed, is that like the same, like if you were to pull the rubber like left to right or like up and down, or is that change like the end on where you pull it?
I mean, if the biaxial or uniaxial, basically it's an equation that's for like low deformation. So as long as it's low deformation, it doesn't matter. Like a balloon is biaxial, chewing gum's biaxial. So it works for those. Yeah, so that's good. I mean, so yeah, I wrote it as a spring constant. So there's a book, actually it's on the webpage called Rubber Elasticity, Traylor's book, which is the original book for this stuff is in Florey's book 1. Then Traylor was a British guy, I think at Manchester, that wrote a book called Rubber Elasticity that came along like 10 years after Florey's book. Then it goes into like exactly how you get all these different kind of moduli from it, like what you're saying. So there's it becomes like tensor math. So it becomes a little bit more complicated to figure out the directions things are pulling. And then people who do computer simulations can model this stuff too in 3D. So yeah, it can get, but the basic thing is like, how's the stuff going to behave? You know, so you expect that you expect the modulus to increase with the temperature. Like it should get that it pulls more. Like if you have a rubber band, it's going to pull back more the higher the temperature. And I mean, the molecular weight and the temperature dependence of the things. And then you got to plug this in. Like if you're going to do a coarse grain model of a polymer, and you're going to have beads, and it's going to be like 10,000 units between it, and you need the spring constant between the beads, then you just plug that equation in for the spring constant. So in terms of simulations, it comes out to be pretty useful to have that. But yeah. I mean, it should apply to like people and proteins and things, you know, it applies to like biological things. Basically, goo behaves that way. But it's not going to apply to metals. In fact, the opposite applies to metals. So it's like the opposite behavior. So ceramics, it won't work. But anything that's like gooey, it's like kind of, they used to call polymer science muck science, you know, so it's like anything gooey is going to behave this way. There's a lot of gooey things, you know, but so anyway, so that plateau modulus is a key part of this thing. That it allows you to that equation allows you to get the molecular weight between entanglements just from that number. Like you just figure out what that modulus is, that immediately gives you, if you measure this with different temperatures, you can get the Kuhn length and the molecular weight between entanglements, which you can use to compare experiments with simulation or something. Or anyway, so it's that business. Then all right, so then what else? Like, what else can you use this equation for? This Gaussian equation, right? So the main use, I mean, one use is that you want to get this R squared thing. Like you want to figure out this R squared. We already showed like you can calculate R squared as in R squared if you do this kind of vector dot product business, where we have the two units. Sometimes they're the same, sometimes they're different. When it's different, it averages to 0. When they're the same, that dot product's 1 because the angle is 0, cosine of 0 is 1. So you just get R squared, and there's n of those. There's n of the I cases, so you get n R squared. But can you get, so you can also get that by saying, well, if you want the moment of the distribution, so the average of some power, these are called moments. So you take the thing you're trying to get the moment of, the power, multiply the distribution, integrate between minus infinity and infinity. And we have this as a probability, so you can plug that in and get R squared, right? It should be possible to do that. And you can match that up with this. Then you can figure out what sigma is here. And what you'll find out is sigma is NL squared, NR squared, right? So, but to find out what sigma is, you have to do this, right? You have to do that integral. So that integral looks like a simple thing to do, but it's actually got some problems because the integral, you need out here d of the argument in here, and derivative of the argument in here is going to be r, not r squared. So you can easily do r exponential minus r squared dr. That's just the integral of the exponential. But you can't do r squared here, right? That's a problematic derivative integral, right? So and you want to get the average R squared so you can use it for this thing. So to get around that, you go, let's see, I want to hide this guy, hide that. So to get around that, there's two math tricks that you need to do, because actually to get this, you need the normalization of the Gaussian, which is that thing, which is also, so dr is not the derivative of R squared, r dr is. So this is also a problem, the normalization factor. And this thing is a problem because it doesn't have r out here, it's got R squared. So to get around that, you do this trick. You do like G alpha, and then you say G alpha squared, but you square it in XY coordinates. So you have X and you have Y. So then all of you have like a Cartesian XY, and this times that is the sum of those. Like you sum the arguments, you have alpha times Y squared plus X squared, you have dx dy. So that's a planar Cartesian XY. If you convert that cylindrical coordinates, then the X becomes R dr and the Y becomes d theta. And then you end up with R squared, and you have an R out here that can be solved. That's the normal integral for an exponential, right? And the two integrals just can become one if you put in the 2 pi for the angular part. And then basically that can be solved. So you can solve that the square of that's pi by alpha, whatever the argument is. The argument's going to be this 1 over k squared. And then the square root of that will give you this integral, right? And then so that's how you get this R squared of that thing. The other thing you get by, and I didn't figure these things out. The guy named DiMarzio at NIST figured this stuff out, but basically, that's who's a smart guy at math. But basically, to get the other integral, like this integral, you have this integral. You realize is a this is the base integral. To get the top integral, you realize that that the derivative of that integral is the integral you want. If you take the derivative with respect to alpha, so the argument, the derivative of the alpha disappears and you just have x squared. The derivative of that with respect to alpha is the thing that you want. So all you have to do is take this thing take the derivative with respect to alpha, and that gives you that thing, which is a thing, this r squared one. And then you can normalize it, then you can do everything you want. Then you can find out that r squared is k squared by 2, and then you know that this thing is also NL squared, so then you can put back in that that this thing is actually this guy. That you can plug in, instead of sigma, you can put in NL squared here. All right, it's a little bit of a math game, but anyway, it's important to kind of go through this because you can skim through, and none of the books actually show you this. So it's like they just say, like there's all the books say like there's this probability function for the distance, and from that you can integrate it and get r squared. But none of them tell you like how you could possibly do that when that isn't a normal integral function, right? So I mean, that's how you do it. Anyway, so this is that business. So yeah, so next time I'm gonna, let's see, Wednesday. Yeah, next time I'll go through a little bit more about what this means, like what that equation means in terms of dimensions and things. So as we're out of time now, I think, but yeah, wait.
I think much more the CPAP. How is the factor 2.15 included in the equation? And how is it determined for that?
It's complicated to get to 2.5, but that's got to do with the geometry of a sphere. So yeah, I don't have that. It's in Einstein's paper on that, the original paper. So I can dig that up and post it. But basically I don't have the answer to the 2.5. The idea is it's a displacement law. So it's like just kind of a simple, it's a simple equation. Yeah. Yeah, don't bother with the 2.5. If you want to get it, you can look up Einstein's paper on it and figure out what he did. But I think it's going to be a lot of, it's not going to be a short thing, you know. So, all right. All right.
There's 2 questions on that homework. Said to like derive.